Hello, my name is Kim Terres, and I will present my research activities performed during a short-term scientific mission of Cost Action FP 1405, titled Production of Biodegradable Packaging by 3D Printing. The collaboration between the LEPAMAP Research Group of University of Girona and PFI Institute within the short-term scientific mission was conducted from 13 of August to 20 of August. The home institution, University of Girona, LEPAMAP Research Group, where I am employed as a researcher, is one of the leading research groups in the field of cellulosic material, nanocellulose, and their uses on composites. The host institution was PFI Institute. This center is an international acknowledged research institute within process and products based on lignocellulose. PFI's focus areas are biorefining and bioenergy, fiber technology and applications, nanocellulose and carbohydrate polymers, and biocomposites. My supervisor on host was Dr. Gary Chinga Carrasco, the head of Biocomposites Department. During the last years, environmental concern has motivated several political and industrial initiatives towards production of environmentally sound and sustainable materials. Hence, several major companies have developed social responsibility strategies with clear environmental focus. Consequently, the biocomposite science community is nowadays very interested in the development of environmentally friendly materials. Their properties, such as low density, non-toxic, low cost, more environmental friendly properties, making them candidates for a multitude of applications. The main advantages of these biocomposites is that natural fibers are easily obtained from renewable resources. The resulting biocomposites offer the possibility to manufacture products relatively easy with good properties, contributing to reduce the potential environment problems. However, the use of biocomposite materials with natural fibers and classic plastic polymers did not solve completely the environmental problem associated with the use of fossil-based materials like polypropylene, polyethylene, etc. Usually, a range of plastic polymer substitution by natural fiber addition was found between 10 to 50% in weight pay. It means that the least the 50% of biocomposite materials is fossil-based. In this sense, the use of bioplastics could help to improve the environmental character of future plastic products. Nowadays, the production of bioplastics is expensive. Addition of natural fibers will be highly beneficial from the point of view of price and mechanical properties. However, the use of natural fibers have some disadvantages, such as the limited processing temperatures below 220 Celsius degrees and the incompatibility between hydrophilic fibers and commonly hydrophobic polymer matrix. The use of malleated polyethylene as coupling agent is a rather attractive method because it avoids the use of expensive and toxic methods. The improvement of the interface between fibers and matrix can lead to optimized physical and mechanical properties of the biocomposite material. In this work, thermomechanical pulp (TMP) fibers from softwood were used as a reinforcement of BioPE. Biocomposites containing TMP fibers from 10 to 30% were formulated and prepared. Furthermore, the obtained biocomposites was used for filament extrusion. Finally, the 3D printability of biocomposite filament was tested for future bio-based packaging materials. TMP fibers, together with BioPE and MAPE, were mixed at different percentage by using an intensive kinetic jelly mat mixer. Initially, the fiber amount was introduced at 300 revolutions per minute for its disintegration. Then, Bio-PE together with coupling agent was added also at 300 revolutions per minute. Finally, the mixing process was carried out during 2 minutes at 3000 revolutions per minute and were discharged when approximately 210 Celsius degrees of temperature was reached. Biocomposite blends containing 10 to 20% of TMP with 0 to 6% of MAPE with regard to the fiber content were prepared. The obtained blends were cut down to small particles in the size range of 10 mm using a miller. The particles were dried and stored at 80 Celsius degrees during 24 hours at least. The obtained biocompounds were used for injection molding dot bonds for mechanical characterization and for filament extrusion for 3D printing. The melt flow index of resulting compounds is useful from a processing point of view. Melt flow index permits to evaluate the influence of natural fibers content on the processability by injection molding, extrusion, or 3D printing of TMP Bio-PE biocomposites. The results shown the evolution of melt flow index when TMP fibers content were increased. As it can be observed, results shows a notable decrease in melt flow index values as the TMP fibers content increase. This reduction of material fluidity implies some adjustments in pressure for injection molding and temperature and time of processing for extrusion or 3D printing. This parameter limits the amount of natural fibers that could be added for a correct processing. The increase in viscosity of biocomposite materials when fiber content increase can be associated with a reduction of polymer chain mobility by its presence. Filament extrusion of pure plastics and biocomposites were performed at a different speed in order to obtain filaments with different diameters for each sample. In both cases, filaments with 30% of TMP present high rigidity, driving to a filament break when it was spooled. The rigidity of these filaments with high content of fibers up to 20% could be controlled by the addition of low amounts of PCl. The use of 5 to 10% of PCl was shown as a useful method to reduce biocomposite rigidity. In order to assess the 3D printability of biocomposites, initially cube samples was performed. As it's possible to see, 3D printing conditions were modified in order to obtain well-defined cubes. Interesting point is the visual cohesion of each sample, important for mechanical properties and also for consumers of future packaging materials. Contrary to the material's viscosities, the introduction of natural fibers in the bioplastic biocomposites promote better adhesion between different layers of 3D printing. Finally, dot bond samples for each material was produced for the mechanical characterization. Difficulties on adhesion of materials in the print surface was caused by the fast cooling of material during printing. In order to solve this problem, special tape was used on the heated printing bed. In this sense, a heating bed temperature between 30 and 50 Celsius degrees was found as the best condition. Currently, other tests are under assessment. Water uptake of samples, morphologic assessment of fibers after compounding by extrusion, electronic microscopy of filaments and 3D printed samples, filaments mechanical testing. Preliminary results show an important decrease in mechanical properties of filaments when they contain TMP fibers. This fact could be associated with an increased porosity in the filaments. Determination by electronic microscopy. Mechanical assessment of 3D printed samples, dot bonds. Preliminary tests show the increase on mechanical behavior when Bio-PE was reinforced with TMP. First conclusions of the short-term scientific mission before the complete finishing of work wear. Incorporation of TMP fibers increases the rigidity of the filaments, and it limits the amount of natural fibers that is possible to add. The use of small amounts of PCl could be an interesting option to reduce the filament rigidity. Biocomposites of bioplastics with natural fibers are 3D printable. The addition of natural fibers on bio-based plastic improves their mechanical behavior and also the addition between 3D printed layers. Bio-PA with TMP are interesting materials to substitute classic plastic on food packaging and to reduce the consumption of plastic from fossil resources. This short-term scientific mission established an important collaboration between University of Girona and RISE PFI to work together in new advances on the food packaging materials using new technologies as 3D printing of reinforced biodegradable materials.